Okay, Bismillahirrahmanirrahim. So today we will be discussing about how to assign demands to the junctions for a network that we have modeled in the previous lectures. So in order to design or in order to assign a demand to each junction, first we should know about the population of that area. So this is some data about the Ghazi-coat. The total area is about 1465 canal, and the total plots is about 1405 in numbers, and the constructed plots is about 850. So these there are three types of residential plots. One canal is about 395 in numbers, while 10 marlas is about 435 in numbers. Similarly, the 6 marlas is about 408 in number. So to design water supply network, first mostly we project the uh, present population to some extent. For example, if you want to design for 25 years or 20 years, so considering that duration, based on that duration, we project our population. So here I'm just considering, I'm simplifying a problem, just considering the total number of plots. So some of the plots are not still constructed, but the rate I will applying will be less, not that much high. That will projected the population, present population very high. So I will be using about 1.5% of increase to project the present population up to 30 years or 25 years. So now I will use the Excel sheet. So the total number of plots are 1405, and per plot I am assuming that the population, average population, is about 7 people per house. Average uh, population per plot. Is about 7 number of population per plot, and so total number of population will be about, by multiplying this number of plots, the average population per plot. So these are the total number of population in that area. Now I have to calculate the per capita or the average demand. So to calculate the average demand, so first I will calculate the projected population. So for I'm taking the growth rate of about 1.5%. So using, so basically according to the WASA, so this geometric growth formula will be, I will be using for the calculating the projected population. So I'm assuming the R is about 1.5% because I'm already considering those plot, that some of the plot that are not constructed. So about 850 plots are constructed, and there are about 1405 plots. So I'm assuming the high value. Therefore, I'm considering a less increase of population. So for example, I'm designing for about 25 years, and I'm also adding a 5 years of commissioning period. So therefore, n value will be taken as 30 years, and the present population we know about that. So based on that, we will project the population. So projected population will be equal to present population into 1 plus the growth, then raised to power 30 years. Okay, so I will round this value. So the total population, projected population, is about 15,373 number of peoples. And the demand, average demand, I will be taking about the so for above this is basically the population is less than 1 lakh, so I will be using 33 gallons per capita per day. So per capita consumption for the specific demand capita per day it's about 33 gallon per capita per day. So to calculate the average demand, so I will multiply the projected population with the per capita. So I will get the average demand. So equal to this multiply this. So about 507,309 is about the average demand, the gallon per day. So this is basically the average demand. So to calculate the maximum day demand, the standard says that the maximum demand is to be taken as 1.5 times the average day demand. So maximum day demand will be about average demand multiply 1.5, and we basically design for the peak hour demand. Therefore, the peak hour demand will be equal to 1.5 times the maximum day demand. So the maximum hour demand will be equal to 1.5 multiplying this value. So this is about the maximum hour demand. So this is the maximum hour demand. So based on this value, we will be designing the water supply network. So we know the population, we know the demand. So now I will be using the GIS in order to construct a polygon of the whole area for the whole network in order to get the demand for each node. So I will be showing you about 3 methods in order to how to assign the demand to these junctions. So first of all, I will create a polygon shapefile. So I am using basically this folder. New and shapefile. Coverage area. Polygon, and the coordinate system is 43 UTM zone 43 north. So I will create the polygon. So after creating a polygon, I will go to the edit, create feature, click on the coverage area, and will approximately So the whole the polygon should cover the whole area, and it will be more accurate if you know about the specific portion of the population of specific portion and construct a polygon for that specific area and assigning the population and the demand to that specific polygon. And I will be showing you that how the demand will be expected from each polygon to each node. So I will just want to show you in WaterGEM. In GIS, most of the guys are difficult for them in order to use GIS, so it make them confused. Therefore, I'm not showing you to manually how to calculate a demand using a GIS. This is the whole area coverage area. So what I have to do, let me edit, modify. Okay, so let me define some attributes for this polygon. So I will create a area field, similarly for a population, and a demand field and a demand field. Area double numeric. Okay. Population double supply longest. Okay. Numeric and the total demand so I will be putting the respective value of in each field. So first of all, I will calculate the area of that polygon. Going to calculate geometry using the specific zone area. Area unit should be in the square meters. Then okay. So it will calculate the whole area. Similarly, the population is about projected to 15,373. 15,373. Supply is about 33 gallon per day, and the demand. So I also want to include the demand, for example, the leakage, and I include the peak factor, but I didn't include the leakage. So I should also consider a leakage, because if you design a water supply network after 1 year, 2 years, then the leakage is, or maybe in the first year, the leakage is started if properly not constructed. So therefore, it should be considered in the design. And most of in the developing countries, that most of the people are not paying for the drawing of water from the water supply network. So this is basically also included in the leakage. So this is basically, I'm taking it from here. Non-revenue water is taking about 20%. So how to calculate a design based on the leakage? So I want to show you the formula. So basically, I'm using this formula in order to calculate the demand calculation. So I explained these parameters in yesterday class, so you can watch that class and able to understand it. So I have also multiplied the average factor with the peak factor with the average demand, and similarly, so L is basically the leakage. So in order to include the leakage, you have to subtract it from the one, and FC is basically the ratio of production divided by demand. So basically, in this case, we are assuming that the demand is equal to the production. So FC is basically taken as 1. So in order to calculate the demand, total demand, I will just 1, 2, or okay. So basically, in order to design a water supply network, I will be using this maximum demand, and in order to incorporate the maximum hour demand. So therefore, I will be inserting a diurnal pattern for each node. So based on that diurnal pattern, I will assume a maximum peak factor for a hour is about 1.5. So it will automatically incorporate there. So I'm not using this value. So these values will be automatically calculating by a software. I will show you that how it will calculate that. So basically, I want to calculate the total demand for the based on the maximum day. Okay, so this is basically the total demand is about 95.205. 9951205 gallons per day. Okay, let me save it. Oh, okay. Now the next step is to import this model into the WaterGEM. So I will import this model. I will import by using a model builder. I will create a new case study using a shape file. Select a data source. So basically, we are using a case study. GIS pipes basically. These are the length of the pipes. So I have already explained each and every step. So no need to explain here. I will just do it directly. So you should properly assign the unit. So you should know about the length of a pipe that you have calculated in the attribute of that in the GIS. So in what unit you have calculated in a GIS, so you should use that unit here. Yes, build the mortal. No. Sorry. Let me first import the junctions. I want to import both at one time. That's how we are. The elevation actually the elevations has not been okay. The junction has been created, but the pipes are not created. Why? Okay. So I will go to the options. Trying I will keep it 0.2 and 0.4. Too small. 5. 0.5. Okay. I will create a symbology. Let me import again the pipes. There's something I'm missing, I think. Okay, establish connectivity using a spatial data. So this should be on in order to import the pipes. Okay. So two missing nodes created at point. Okay, 190 pipes have been created. Yes. So the pipes has been created automatically. Okay. So you can observe the pipes and the junctions. So now I want to relabel the pipe's name. Oh my. Okay. I want to really relabel all of these pipes. So I want to renumber and giving the prefixes P dash. So the all number will be relabel, and the length has been calculated automatically and assigned to each pipe for model builder. So the diameter will be designed inshallah when I start the lecture of designing a pump in for a water supply network. So for after that we will design the diameter of each pipe. So here I am using a ductile iron pipe, or maybe use a galvanized iron pipe for a design. So similarly I will label a junction table as well. Relabel. So all the junctions is now be relabeled. So now the elevations are not have been assigned to each junction. Therefore, I want to assign these elevations. Okay. So I will be using tracks, the DXF contours. The file is in the WMS folder. This is the Ghazi-coat surface. Select elevation field. It should be elevation, and the XY unit are in the meters, and similarly the Z units are in the meter. If the DXF file or the surface unit or the units are in meters, and you are using here a feet and something else, then it will not work correctly. Therefore, the unit should match with the surface. So now the units has been assigned to each junction. Okay. So what I have to do? So I have to assign a demand to each node. So for that, I have to construct first a Thyssen polygon. So I will explain it to you that what are the Thyssen polygon. So I will create for a junction the Thyssen polygon, boundary layer. I am taking the boundary layer which I have created, the coverage area. Output file should be saved as the TP Thyssen polygon. So now the Thyssen polygon have been created. So let me open the Thyssen polygon. I want to change the color of that. Okay, green. So basically, what the software did, it uses the GIS polygon that I have created earlier, and basically what it does, let me open the one more. Okay. For example, I have a node here and I have a node here, and then these nodes are connected with each other using a pipe. So the Thyssen algorithm in WaterGEM or in a GIS, basically a Thyssen polygon, this algorithm of GIS. So what it does, it draws a perpendicular to this pipe. And for example, if there is no pipe here, it assumes that, and similarly drawing a perpendicular here, and I'm assuming for example, there's the polygon, the boundary polygon I'm assuming here. So up to that, so for that node, this area is the polygon. Similarly, the perpendicular are drawn by the WaterGEM or the GIS to this pipe. So based on this pipe, connecting this perpendicular to this pipe, and similarly for this pipe, so the area, this area basically is assigned as a Thesan polygon to this node, and similarly for this node, this polygon is assigned as a Thesan polygon to this node, and similarly this polygon is assigned to this node. So what it does, basically, it will do calculation in such a way that the area of that polygon will be multiplied with the density layer of, or the demand we have written in here, the attributes, and based on the area, the demand will be assigned to each node. So basically what it will do, it will first calculate the density. For example, I want to show you that in a GIS attribute table. First, the method I am going to use, that method will use the population will be divided by the area. So it will it will calculate the density by dividing the population by area. So by using that value will be multiplied with the each polygon area, and then it will multiply with the demand, supply demand. So based on that demand, the demand will be assigned to each node. So I'm using so you can observe this. Basically the Thesan polygon has used the boundary of a polygon which I have constructed earlier. So based on that boundary, it has calculated the Thesan polygon for each node. So now I will use a load builder, create a new method. So there are the different method. Point load data basically are using, for example, if you have a billing data or meter data in a shape file, so you can use billing meter aggregation and nearest node, nearest pipe method. You can assign that meter data to each node. So here I have not that data is not available with me. So if, for example, if you have a meter data in a shape file, then you can easily assign demands by using that meter data in the form of shape file in order to get the demand for each junction. So here I will be showing you the proportional distribution by area in order to design a demand. So you can observe by the figure as well by using a Thesan polygon. So the service area layer will be the Thesan polygon I have created, and the boundary layer will be the polygon, the coverage area, and the boundary field will be the demand, and the supply field will be the thing, basically this one. And the boundary field will be the demand, and this is basically in gallon per day. I think it should be, where is it, it is per capita per day. So gallon per capita per day, so it is basically in gallon per day. So this unit should be correct. Otherwise, it will give you the incorrect result, wrong demands. So these field should be assigned to that specific field. So the boundary field should be assigned to that demand field, and the flow field should be assigned to the average demand or the specific demand field. Going next. So this multiplier basically, let me convert this unit to the gallon per day. So the consumption is about 33 gallon per day. 33 gallon per day the sinapakar. Sama the supply equal wadi on the demand. Now, okay. So the boundary field should be the supply field, and the flow field should be the demand field. Based on that demand field, it will calculate the consumption. So you can observe that it is approximately, they have calculated the consumption. So multiplier basically the 1.5 maximum day peak factor or maximum hour factor. So for the maximum day, I have already calculated that multiplier. So the pattern I will show you that how to design patterns and what are patterns. Basically, I have explained the patterns, the diagonal patterns in the previous class. So here I will just assigning these patterns. The assumed pattern basically in Pakistan, that no one have did a research in order to calculate the patterns for specific area. Basically, the patterns varies from area to area, and basically it's also varies from city to city and from uh, district to district. So it also varies from country to country. So in Pakistan, that patterns are basically not calculated, not found. So I will be assuming a pattern, and that pattern will be assigned to each node. So next, so you can observe that the demand for each junctions have been calculated. Okay. Next label is GIS method. New alternative GIS demand. So I'm creating a new link. So it's going to end. So the demands have been uploaded. So I want to show you. Let me save it and stop sharing.